I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth.
Picking up some dust.
In the 1960s, an impossible dream came true when human beings walked on another world.
The Eagle has landed.
In all, 24 Americans went to the moon. But it took an unseen army of over 400,000 engineers and technicians to make it possible. This is the story of the men and women who built the machines that took us to the moon. (1961). Russia is winning the space race. The only way to get U.S. astronauts into space is on top of a nuclear ballistic missile, its warhead replaced with a tiny Mercury capsule. There is just enough room inside to squeeze a solitary astronaut in his pressure suit.
5, 4, 3, 2, 1, fire.
NASA astronaut Gus Grissom rode the second Mercury capsule into space on the 21st of July, 1961.
Okay, the fuel is go. About 1 1/4 G's. Cabin pressure is just coming off the peg. The oxygen is go.
But his 15-minute suborbital flight nearly ended in disaster 300 miles off the coast of Florida. Moments after splashdown, there was an explosion. The hatch prematurely blew off. Water poured in, and in seconds, the capsule was sinking. Grissom was lucky not to go down with it. His flight had shown just how vulnerable an astronaut was to the slightest malfunction in his spacecraft. It was a salutary reminder for the thousands of engineers who were gearing up for a challenge much greater than the Mercury program, Project Apollo.
I'd started work at NASA here in Houston in June of 1962. President Kennedy made a speech in the stadium at Rice University in September of 1962. So after only a few months, here I was sitting in Rice Stadium with the President of the United States when he made the speech where he said we were going to the moon by the end of the decade. And at that time, young as I was, that was quite a challenge.
We shall send to the moon, 240,000 miles away, a giant rocket more than 300 feet tall.
I mean, it just was unbelievable.
To go to the moon and back would demand a much bigger spacecraft than Mercury, and one which would allow the Apollo astronauts a much greater degree of control, a spacecraft they could really fly. In fact, for 3 years, NASA had been flying to the edge of space in the X-15 rocket plane.
And I think that really impressed NASA. NASA had been a co-funder of that program with the Air Force. And the NASA people loved it, and I think they loved the people that worked on it.
The X-15 was built by a company called North American Aviation.
They were very much in the aircraft business, and we felt that the Apollo had to be thought of as a flying machine with men flying it. And it was on that basis that we picked North American.
But the engineers at North American soon realized that the Apollo spacecraft would be far more complex than anything they had built before.
When you break it down by functions, by what you have to do step by step, then you see what you actually have to do. You needed a propulsion system. You needed an environmental control system.
Oxygen and water. The food supply.
You needed a heat shield.
A parachute to bring them back to Earth.
Human waste disposal.
You had shaving supplies, you had hygiene.
A window to look out of.
We also had to look out for micrometeorites.
Had life preservers, had a couple machetes.
The command module was a little tiny house for 3 people.
North American started by building wooden mock-ups to get a feel for the layout of the new 3-man spacecraft.
Getting 3 people to live in that little house for 14 or 15 days became a pretty difficult project.
The engineers were faced with a dilemma. A spacecraft large enough to sustain 3 men all the way to the moon would be too big to safely return to Earth.
If you put everything you need inside the command module itself, it becomes quite large and heavy. And when you plan to re-enter back into the Earth's atmosphere, a large, heavy vehicle is not desirable.
The heavier a spacecraft, the more energy it has when it hits the Earth's atmosphere, and therefore the more heat it will generate as it slows down. A fully laden Apollo spacecraft would simply burn up. But North American realized that not everything that went to the moon needed to come back to Earth. The answer was to split the Apollo spacecraft in 2.
So the solution to the problem wound up having essentially a 2-module concept, the service module and the command module. The service module was like a trailer behind the command module, and it was attached to the command module during launch, stayed attached all the way through the trip to the moon on the way back, and just before re-entry, the service module would be jettisoned.
The service module would carry almost everything the crew would need to keep them alive for the duration of the mission.
It has the propulsion system, it has the fuel cells for the power, it has the oxygen and hydrogen tanks that are the reactants for the fuel cells, and it's got, of course, the engine.
With much of the weight of the spacecraft in the service module, the Apollo capsule would now be small and light enough to survive re-entry. But there wouldn't be much space for the 3-man crew to live for 10 days.
If you look at it very simply, it's about a 6 by 6 by 6 cube. That's what you're living in.
By 1964, America's astronauts were being introduced to the new spacecraft that was meant to get them to the moon by the end of the decade. But as impressive as these prototypes looked, for the engineers at North American Aviation who were building the Apollo command module, there was still a lot that needed to be worked out. The most fundamental thing the spacecraft would need to keep 3 men alive for a 10-day journey to the moon and back was going to be electrical power.
There's several ways of providing power on a spacecraft. One is batteries, but batteries, as you know from your use in a car, are quite heavy, can be quite large. Also, you can use something like solar panels, which some of the unmanned spacecraft use going to the outer planets that have to operate for a long period of time. However, they get quite heavy and take quite a large area, so the solution for the problem was to use fuel cells.
The clever idea behind the fuel cell was to use the same hydrogen and oxygen gases which powered the spacecraft's rocket engine. In the rocket, the gases reacted together, creating heat and pressure to push the spacecraft forward. But in the more controlled environment of the fuel cell, the same reaction could produce electricity.
Fuel cells have a lot of desirable characteristics. You can take the oxygen gas and the hydrogen gas that are stored in tanks, combine those together through the fuel cell, and you get water as a byproduct along with the electricity that you want. The water is desirable. You can use that for drinking. You can use it for cooling through the environmental control system. So it turns out it's a byproduct, but it's a very useful byproduct.
In fact, the water that the fuel cells produce is something like on the order of 50 or 60 gallons during a mission. So they produce a lot of water.
But wiring and plumbing all this equipment into the spacecraft started to cause its own problems. The task needed almost 40 miles of cables, which added a lot of weight. They also took up a lot of room. Something else had to shrink, and so attention turned to another vital part of the life support system: food. NASA figured that if they were going to be making so much water with the fuel cells, then there was no need to also carry a load of water in the food as well. So, by mincing and then dehydrating the meals, they could be compressed and reduced in weight and size before being packed for the flight.
This food package was day 9, meal B, and they were all packaged with a bunch of different items in the meal. For example, this was a tuna salad package, and the way this operated was the crew took a water gun and insert the nozzle into the food bag and squirt 3 ounces of water into the bag, massaged it, and I think for so many minutes, and then it was ready to squirt into their mouth to eat.
This space diet was designed to minimize the production of solid human waste. Initially, the spacecraft designers were optimistic that the entire 10-day voyage to the moon and back could be carried out without a single restroom break. Jerry Goodman was asked to test the low-waste diet.
I was a test subject for the Apollo food when it was first developed, and I took home a supply to keep me to eat for 14 days. So I did that, and as a result, I had a very big problem. And it was kind of like having a baby. And I remember afterwards, at the end of that, I delivered the baby to the guy that was running the test program.
It was clear that there was no avoiding the simple fact that what goes in must come out. But it was equally clear that there was no room aboard the spacecraft for a lavatory.
There was no bathroom as you and I know it. There was no cosmic commode as you and I know it. If you were going to the moon at 25,000 miles an hour, you'd say, excuse me. You'd float off your seat, of course, and you open this outside pouch up, and inside was another little bag, and this is it, voila.
While one set of engineers were grappling with what went on inside the command module, another team at North American were working on the outside. Would it be tough enough to survive the rigors of a flight to the moon and the return to Earth? It was time for the capsule's first flight. The drop tests demonstrated how dangerous a hard landing could be for the astronauts. A water landing seemed like a better bet. But a splashdown came with its own problems, as the first test revealed.
Water landings were conducted in a slightly different way. We had something that would be very similar to a child's swing. And in place of the child, we would have the Apollo spacecraft.
This was that big tower there in Downey, and we swung the command module, splashed down, and we were all so happy seeing it there floating, and suddenly we saw that's getting smaller and smaller and smaller. It was sinking. I remember that was one of the darkest days that we had in the beginning.
The capsule's belly flop had cracked its outer skin, allowing water to flood in. It was hugely embarrassing for the engineers.
We were devastated. I was specifically devastated because this could lead to a delay in the total Apollo program.
What terrified everybody was a repeat performance of Gus Grissom's near drowning when his Mercury capsule had sunk after splashdown. The thought of 3 men returning safely from the moon only to drown in front of the world's press was unbearable. So the command module's new, stronger outer shell was exposed to some of the most rigorous testing of the whole Apollo program.
The instrumentation included cameras underwater, cameras external, cameras to record the conditions. It was a test program that was to truly verify that we would have a successful landing.
The water tests proved that the command module could survive splashdown. But what about liftoff? During launch, the spacecraft would be sitting on top of the Saturn V booster, filled with over 3,000 tons of highly explosive fuel. So the engineers designed a sort of ejector seat for the whole command module in case anything went wrong.
The launch escape tower was a rocket at the front of the command module that would pull the command module away from the booster if there were a problem with the booster.
The system would be triggered by 3 wires that ran down the entire length of the Saturn V booster.
If we would lose power on 2 out of 3 wires, that signified that the booster is falling apart, and we would just get off.
In November 1965, the North American engineering team gathered to witness another make-or-break test. A rocket called Little Joe was to be used to test the launch escape system.
The idea was to launch it up to about 10,000 feet, then fire the escape rocket to pull the command module away from the other device.
1, fire.
This time, they had made a little mistake in how they hooked up the roll gyros. And the vehicle started to roll. When it broke the link on the escape rocket. The escape rocket fired, pulled the command module right off the top. And it was a perfectly successful flight, very well instrumented flight, gave us all the data we needed about the launch escape system, but the vehicle had failed in the process.
Ironically, the unanticipated failure of the Little Joe rocket provided the best possible test for the escape system, and it had performed perfectly. But as the engineers celebrated, events were about to take a tragic turn, one which would throw into question every aspect of their new spacecraft. January 1967, and the new Apollo spacecraft was going through its final tests before its maiden manned flight into space.
Apollo 1 was going to be our first true Earth orbital test of the vehicle. It was really to understand the interface with the astronauts and the spacecraft. So it's really what you would call a shakedown mission prior to leaving the gravitational field of the Earth.
The command module was an early design known as a Block 1. As with any prototype, it had its teething problems. But the flaws with this spacecraft were more serious.
The Block 1 vehicle was not lunar capable, and because of the pressure schedule, I think there were things that were not done quite perfectly in it.
We didn't really have the kind of focus, I thought, in retrospect, that we should have had.
So we had a lot of problems in the qualification testing of the hardware throughout the system. And they were not a good foundation of confidence to go to the moon.
Mission Commander, Mercury veteran Gus Grissom and his crew of rookie astronaut Roger Chaffee and America's first spacewalker Ed White were not happy either, openly mocking the command module's reliability during a pre-mission photo shoot. At 1 p.m. on January 27, 1967, the crew ascended the launch tower and prepared for a routine pre-flight test in the capsule. But there was something extremely dangerous inside the spacecraft, something that no one had noticed.
The environment in the cabin at the time was 100% oxygen at 16 pounds per square inch.
Such high levels of oxygen had been pumped into the command module to help seal the inward opening hatch against the outside air pressure. But no one had considered the possible consequences of an atmosphere of 16 pounds per square inch of pure oxygen.
The crew was going through their test. There's a test procedure that you go through. You activate all the systems. You basically activate every system you have in the vehicle and down to 0, but you don't ignite the engine.
At 6:30 p.m., with the simulations dragging on into the evening, a glitch in the capsule's electrical systems was detected by launch control.
Somehow we got a spark. We don't know how that spark occurred, but there was a spark. And at 16 psi, everything burns. Aluminum burns. All the insulation on the wires burn. All the wiring burned.
And with an inward opening hatch, the astronauts cannot open the hatch.
And the crew perished because of that.
One by one, wherever they were around the country, the engineers heard the news.
And a highway patrolman stopped and said, is there Mike Vucelich in the car? I said, yes, it is me. He said, you call your control center. I said, what's the problem? He said, I can't tell you.
By the next day, many of the North American engineers had reached the Cape to see for themselves what had gone so badly wrong.
They had gotten to the place where they had the hatch open by the time I got there. And it was a disaster. We didn't have much to say, neither NASA or us at the time.
That was a very hard time for me. I almost felt responsible because I was the guy that was associated with the oxygen and the like.
It was very, very difficult situation, and I felt responsible in some ways. All of us were shocked with how easily things burnt in oxygen, high-pressure oxygen. Stuff.
While everyone struggled to come to terms with what had gone wrong, all future Apollo missions were halted. NASA began a detailed investigation, and rather than put an engineer in charge, they appointed astronaut Frank Borman. The fate of Apollo was in his hands.
Working with Frank Borman was a pleasure. He was so intuitive, he was so aggressive, he was so, let's get the job done. I can't tell you how wonderful. It was one of my highlights of my career, working with Frank Borman in that activity.
I was really impressed by determination of the NASA to find the causes and then get on to correct them.
To their dismay, the investigators found that things had become so rushed in the time before Apollo 1's test flight that there weren't even complete paper records of what had been installed inside the spacecraft.
I think it woke a lot of us up. It did me. But it also said that this is not just a job, it's a very, very important job. It means people's lives. So I ended up being probably rededicated. I felt like a warrior. And I still call myself an Apollo warrior. I don't mean in a sense of killing people. I mean a sense of getting things done. And I think the team ended up like a lean and mean group of Trojan warriors.
Ironically, the inward opening Apollo hatch, which had trapped the astronauts in the burning spacecraft, had only been specified as a safety measure after Gus Grissom's Mercury hatch incident 5 years before. The investigation also confirmed that the wiring was dangerously exposed and a great deal of flammable material had crept into the command module's design. Combined with the high-pressure pure oxygen atmosphere, these materials hadn't just burned, they'd exploded. A major redesign of the command module was needed.
From a technical point of view, I think the fire had a very beneficial final effect on the program. It enabled the program to stop and review exactly where we stood on every element in the system and to fix every problem that we saw in the system.
We changed to an outward opening hatch. We put in floorboards that we didn't have previously. We changed the air system to where it was 60% nitrogen, 40% oxygen when you were on the pad. All those things were done in about 18 months.
With the redesigned and improved spacecraft, the Apollo program was back on track.
We were dedicated to what we had to do. We were in a space race with the Russians. We were in a spotlight, and we couldn't falter again, and we couldn't kill people again.
Everyone was determined that the deaths of Gus Grissom, Roger Chaffee, and Ed White would not be in vain. It was time once more to reach for the moon. October 1968, and Apollo 7, the first manned Apollo mission, was on the launch pad at Cape Kennedy. The fire had set back the moon program by 18 months. There was now just over a year left to reach the moon.
Here we were flying in October of 1968, and we had to make it by the end of 1969, and it was a short time.
All the forces at North American had been working on the spacecraft 24 hours a day, 7 days a week, since that fire, to get the spacecraft in a configuration we had confidence in for flying.
The mission was very much like Apollo 1. It was really a shakedown cruise of Earth orbital mission to really shake the vehicle down and get the compatibility of the systems with the crew.
You know, you don't get many opportunities on the ground to test at zero-G. And so it was a really important flight for testing all the equipment.
5, 4, 3, 2, we have ignition. Commit liftoff. We have liftoff. This is launch control. We have cleared the tower.
Roger, tower clear. 12 seconds out and the roll program has commenced.
On the morning of October 11th, 1968, the new Apollo Command Module lifted off the pad.
4 seconds out, and Schirra reports the pitch program has commenced.
On board was Mercury veteran Wally Schirra with rookie astronauts Don Isley and Walter Cunningham. It was the first time 3 Americans had flown into space together.
We're having a status check. Apollo 7 has been given a go for staging.
As the rocket's first stage fell away, the second stage ignited, hurling them the final few miles into orbit. In zero gravity, the cramped command module took on a new, more roomy feel, and through a wide-angle lens, it appeared positively spacious. It was the first time any humans were able to float around in zero gravity unencumbered by spacesuits. The crew had 11 days in Earth's orbit to subject the command module to a thorough test, and the engineers knew Commander Wally Schirra was going to be a hard man to impress.
I remember particularly he was religiously interested in making sure the command module was clean. when it flew, because everything that was loose would come floating up into the command module. And he had had trouble with that in the other two vehicles. So we really worked over the cleanliness of the command module. And when he got back, he gave me a little piece of plastic within which was a little piece of beta cloth that had floated up in front of him during the flight. It was, I think it was the only piece of floating debris that he had found in the whole flight. We were pretty pleased about that.
On its maiden manned flight, the Apollo command module had exceeded expectations. From the fuel cells to the cabin environment and atmosphere, every life support system had performed to perfection. Even the infamous space food and the basic restroom facilities had proved bearable. With every engineering milestone passed, all that was left was re-entry.
Okay, it's been real fine, Walt. Just a final update on the weather and the recovery area. 2,000 broken, winds 270 at 20, wave height is 3 feet.
For any capsule re-entering the Earth's atmosphere, three things mattered more than anything else.
Parachutes, parachutes, parachutes.
There's no other part of the command module and service module that I worried more about than all three of those parachutes getting open during landing.
NASA had been developing parachutes for returning spacecraft since the days of its Mercury flights. But when it came to developing a parachute system for the new Apollo spacecraft at the North American factory in Downey, California, there was only one man for the job.
I was the only one in the corporation of North American Aviation that had parachutes written on his badge. So I was the logical one to be rounded up and brought into Downey to where the biggest parachute activity would be.
Apollo parachute testing started with models in a giant vertical wind tunnel.
What we had to achieve with this parachute system was extreme reliability. And my job was to take it from an idea to an operating system. We made 137 drop tests throughout a period of 6 years.
A returning Apollo capsule would deploy its first drogue parachutes while still 25,000 feet up and traveling at 320 miles an hour. Then at 10,000 feet and still traveling at over 160 miles an hour, the main chutes would be opened. For a safe landing, these giant canopies would need to survive unprecedented speeds without shredding, to slow down the spacecraft to less than 20 miles an hour.
No program before or since has ever had a parachute that was so thoroughly tested.
With the designs perfected, it was time to manufacture them.
There's approximately a half acre of very lightweight nylon fabric. We call it ripstop. In each main parachute, there's approximately 2 million stitches. The suspension lines are 1.5 miles long. It takes about a week to pack this very, very, very tightly under hydraulic presses. And when we finished, the density of the fabric was like maple wood. These ladies took great pride in what they did. They all seemed to understand more than many of us that their sewing was the last important step in returning these astronauts safely home.
On the 22nd of October 1968, after 11 days in space, the first astronauts to ride the Apollo command module returned to Earth on the finest parachutes ever made.
Everybody sees the parachute system. It puts on a good show. On Apollo, it occurred at the last moment when all the world was looking. So it made it very rewarding and very satisfying to be a part of that industry.
Wally Schirra and his crew had test-flown an almost flawless command module in Earth's orbit. Before the year was out, a new crew would take it on arguably the most historic flight ever undertaken by man, from the Earth to the Moon. It was the autumn of 1968, and at North American Aviation's factory in Downey, California, engineers were preparing the Apollo spacecraft for a second test flight in Earth's orbit. But things were about to change.
We were asked the question, did we think the spacecraft was ready to undertake a mission around the moon?
A figure 8 around the moon. Apollo 8 around the moon.
It was going out where we'd never gone before with a manned mission. Very risky, but could really pay off with a lot of excitement.
Apollo 8 coming up on 20 seconds to ignition. Mark it, and you're looking very good.
The engineers were confident their spacecraft was ready to go to the moon, and so the crew of Apollo 8, Jim Lovell, Frank Borman, and Bill Anders, became the first men in history to leave Earth's orbit. Their safety and comfort depended on an environmental control system designed to cope with the most extreme environment ever encountered by humans: deep space.
You can go from plus 250 degrees Fahrenheit down to minus 250 degrees Fahrenheit, and it can happen just as you cross the line of a shadow, for example, on a spacecraft. So you can instantaneously go from one extreme to the other and have like a 500-degree Fahrenheit change.
For 3 days, everything went well. But as they neared the moon, something unexpected happened.
The spacecraft temperatures suddenly started to drop well into the mission. And everybody in the spacecraft was getting pretty cold. And we thought that perhaps our environmental control system was not meeting the requirements. But what had happened was, for the first time in our flight experience, we had gotten into the shadow of the moon. So suddenly we were in the dark, looking at dark space, and that was the cause of the spacecraft temperature suddenly dropping, and I mean dropping at a great rate. So that was another great experience.
With every second that passed, the command module was making history, carrying its crew farther from Earth than ever before.
Apollo 8, Houston, 1 minute to LOS, all systems go. Thanks a lot, troops. See you on the other side.
We were concerned, and of course, when we went in the backside of the moon, we were really concerned because we couldn't hear and communicate with the crew, but we had our fingers crossed all the time.
It was Christmas Eve, 1968, and across America, the 40,000 men and women who'd worked on the Apollo command module stopped and watched in awe.
I personally remember having my Christmas vacation with my parents and my new wife. My dad set the TV up on the counter where we could watch it during the Christmas dinner. And Apollo 8 had pretty good TV coverage compared to previous missions. So for the first time, we were getting real-time TV that we could watch while the mission was going on.
And from the crew of Apollo 8, we close with good night, good luck, a Merry Christmas, and God bless all of you on the good Earth.
And you could see the surface of the moon as they were going around. You saw these views, just unbelievable. And you know, the environment I was in with my parents and my wife, it was just amazing.
For the engineering teams at Mission Control, Christmas was a rather hurried affair. Their Apollo spacecraft and its crew were 250,000 miles away from Earth. To get them home, they knew the service module's rocket motor would have to perform perfectly yet again.
SPS is a service propulsion engine. It's on the elements of the back end of the service module with a big bell nozzle. That engine gets you into lunar orbit. It also gets you out of lunar orbit. If that engine failed and doesn't get you out of lunar orbit, you can't get the spacecraft back to Earth.
3 minutes LOS. All systems are go. Over. Roger, thank you, Houston. Apollo 8.
The crucial engine burn to bring them home would take place on the far side of the moon, when the spacecraft was out of contact with mission control for 45 minutes. The engineers wouldn't know if everything had worked until the spacecraft reappeared.
Somebody asked Frank Borman, what if that engine doesn't work? He said, it's a bad day. And that was the longest 45 minutes of my life.
Apollo 8. Apollo 8. This is Houston. Apollo 8. Apollo 8. This is Houston. Houston, Apollo 8, over. Hello, Apollo 8. Loud and clear. Roger. Please be informed there is a Santa Claus.
I felt that's probably one of the highs that I felt during the Apollo program, that we had pretty much pulled it off.
As Apollo 8 pulled away from the moon and began to free fall back towards the Earth, Jack Clemens and his team of re-entry specialists got to work.
My job for re-entry started at the moon with that first burn. They're now in contact with the Earth again. Almost immediately then, after that, we take that information and we start running simulations down on the ground to say, well, where's that going to bring them?
The returning Apollo 8 command module was effectively free-falling back to Earth from 250,000 miles away, and they would be re-entering the atmosphere much faster than Apollo 7 had done. There would be no second chance to get it right.
Apollo 8 had a lot of effect on us emotionally in terms of how well have you done your work, because this is the first time we're coming back from the moon at all, and you want to do it right.
The command module would be traveling at 25,000 miles per hour when it hit the upper atmosphere.
If you travel down the highway, you're traveling at 60 miles per hour, you're traveling at 88 feet per second. We're coming in at 36,000 feet per second.
It smashes into the atmosphere. It doesn't fly as much as smash.
To protect the capsule, the engineers had built the largest heat shield ever. It was designed to disintegrate as the heated atmosphere tore into it. But to safely return the crew, the command module would have to re-enter at exactly the right angle.
If you came in too shallow, coming in and not gathering enough drag from that from the shallowness of the atmosphere to slow you down, so you'd keep going right through the atmosphere and out the other side. If one came in too steep, this was more like a belly flop off a high diving board into a pool, because the atmosphere, for all its fragility when we're walking through it, when you're coming in at Mach 30 or so, it's very dense. And if you hit it too deeply, you could break up the command module itself. So everybody was highly motivated to sort of stay in that boundary.
The command module needed to maneuver in the upper atmosphere, but it was not easy to steer a blunt capsule traveling so fast.
The way we steer the command module is little reaction jets here that roll this vehicle. The only thing, it can't turn this way, it can't turn this way. All it can do is roll a little bit about this axis. It's a very rudimentary control mechanism, but it worked.
For those watching and waiting through the night on Earth, the tension was made worse by the radio blackout caused by the heat of re-entry. Along with everyone else, the engineers were also left wondering how things had gone.
The big event that happens to a re-entry specialist on Apollo is crewmen on one of the aircraft carriers picking up the chutes in their camera, because that means everything. That's when the pressure's off. When we see those chutes open up, and it's like, we got it, we're there.
The first astronauts to ride the command module all the way to the moon returned triumphantly 3 days before the end of 1968. North America's engineers had proved that their capsule could carry men to another world.
It was really a big jump in getting us ready to go land on the moon. It was really, to me, the most significant event that we were able to do to get ready to land on the moon.
Over the next 4 years, 8 more Apollo command modules would fly to the moon, carrying a total of 24 Americans into lunar orbit and safely back to Earth. They were the only Apollo machines to return and rest today in museums around the world as a tribute to the 40,000 men and women who built them.
We had a great group of people working Apollo. We really got down to work as a team and had a terrific camaraderie, I think, cooperation. And it was a wonderful experience to live through. I wish I could thank everyone and hug them.